Welcome back to The Explainer. So today we're diving into something that I absolutely love. You know, when a lot of us hear the word chemistry, we instantly picture like crazy abstract math or some isolated sterile laboratory. But honestly, chemistry is this incredibly dynamic, totally observable language that just describes the everyday world right in front of us. It's literally the source code for how matter interacts, changes, and transforms. So buckle up, because we're going to decode the matrix of matter together.
Okay, let's start here. What do a rusting iron pan left out in the damp air, the food you're digesting right now, and grapes fermenting in a vineyard all have in common? I mean, on the surface, they seem completely unrelated, right? But the shared secret here is that in every single one of these situations, the actual identity of the initial substance has fundamentally changed. They just aren't what they were when they started. And whenever a switch-up like that happens, boom, you've got a chemical reaction.
So here's our roadmap for today's explainer. We're going to hit the clues of chemical change, how we write the chemical code, balancing the chemical ledger, and finally, the different types of chemical reactions.
All right, part one, clues of chemical change, spotting the evidence.
Think of this whole thing like a detective story. If these chemical reactions are happening all around us all the time, how do we actually know they've taken place? Well, we have to look for the physical clues. And there are four main ones to watch out for. First up is a change in state, like a solid suddenly becoming a liquid or a gas. Second is a change in color. Third is the evolution of a gas, which you'd usually see as bubbles or some kind of fume. Like if you were to heat lead nitrate powder, you'd immediately see this sudden burst of really thick brown fumes of nitrogen dioxide. It's a dead giveaway. And the fourth clue is a change in temperature. If you've ever seen a magnesium ribbon burn in the air, you know it erupts into this dazzling, super hot white flame and leaves behind just a white powder. If you catch one or more of these four things happening, yup, you've just caught a chemical reaction red-handed.
Moving right along to part two, writing the chemical code, from words to symbols.
Okay, so we spotted our physical clues. But writing out magnesium burns and oxygen to create magnesium oxide every single time we do an experiment, yeah, that gets really clunky really fast. Science is all about precision and efficiency. So on the left side, we have a basic word equation. It gets the job done, showing the reactants on the left of the arrow and the product on the right. But check out the right side. By swapping out those words for chemical formulas, the whole thing becomes this incredibly concise, universally understood code. Mg plus O2 yields MgO. It's sleek, it's fast, and it perfectly captures the whole shebang.
Which brings us to part three, balancing the chemical ledger, the law of conservation of mass.
So there's this absolutely crucial rule in our chemical matrix called the law of conservation of mass. Basically, mass can neither be created nor destroyed during a chemical reaction. The total mass of the ingredients, the reactants, has to perfectly match the total mass of the products. The ledger has to balance. But take a look at this setup for iron reacting with water. Notice how the atoms of iron, or Fe, and oxygen, O, are totally lopsided when you compare the left and right sides. We've got one single iron atom going in, but three somehow coming out. Since the mass doesn't match up, this is what we call a skeletal or unbalanced equation, and we really need to balance this ledger.
To fix this, we use something called the hit and trial method. Honestly, it's just like a giant accounting puzzle. Step one, we imagine drawing boxes around each formula. And this is super important because you absolutely cannot mess with the actual chemical formulas inside those boxes. You can't just magically change H2O to H2O4 just because you want more oxygen. Instead, we list out our atoms, find the compound that has the most atoms to start with, and we just start testing things out. We place the smallest possible whole numbers, our coefficients, in front of those boxes until both sides of our ledger match up perfectly.
And here is the final result of that hit and trial puzzle, our beautifully balanced equation. We've now got 3 iron atoms and 8 hydrogen atoms on both sides, fair and square. But hey, do you see those little letters in the parentheses? We've also added physical state symbols. S is for solid, G is for gas. In this particular reaction, the G right next to H2O is actually telling us that the water is being used in the form of steam. Adding those tiny little symbols makes our chemical code incredibly rich with information at just a quick glance.
All right, part four, types of chemical reactions, the reaction roster. Now that we know how to spot these reactions and write them down, let's categorize them. We're going to look at the distinct ways these elements actually behave, how they break apart, and how they rearrange their bonds. Let's meet the suspects on our reaction roster. First up is the combination reaction. Just like it sounds, this is when two or more substances just join forces to form one single product.
A really great example of this is calcium oxide, which you might know as quicklime, reacting with water. When you mix them, they combine super vigorously to form a single product called slaked lime. But check out that word heat tagged on at the end of the equation. This reaction releases a massive amount of heat, making the whole mixture really warm. Whenever heat is released alongside the products like that, we call it an exothermic chemical reaction.
Now, let's look at the exact opposite scenario, the decomposition reaction. This is where you have a single reactant that literally just breaks down to give you two or more simpler products.
A perfect illustration of this one is the decomposition of calcium carbonate, better known as limestone. When you hit limestone with some intense heat, it actually breaks apart into quicklime and carbon dioxide gas. Because it's that extreme heat driving the breakdown, we specifically call this a thermal decomposition reaction. And by the way, this isn't just some neat little lab trick. This exact reaction is a massive industrial process used all over the globe to manufacture cement.
Next on our roster is the displacement reaction. I kinda like to think of this one as a dance, where a stronger, much more reactive element boldly cuts in, takes the place of a weaker element in a compound, and effectively just kicks it right off the dance floor.
And this one creates a really striking visual. If you take some shiny iron nails and drop them into a bright blue solution of copper sulfate, a displacement reaction kicks off. See, iron is a lot more reactive than copper. So over about 20 minutes or so, the iron actively displaces the copper right out of the solution. The result? It's awesome. That bright blue copper sulfate solution completely fades out and your iron nails get coated in this very distinct brownish color from the displaced copper.
All right, our final category for today is the oxidation reaction. This one is purely focused on the simple, totally observable addition of oxygen to a substance during a reaction.
For example, if you take some copper powder in a dish and just heat it up, it reacts with the oxygen right out of the air. The surface of that copper powder will quickly get coated in this black substance. That black stuff is copper oxide. Oxygen has literally been added to the copper, beautifully and simply showing us oxidation in real time.
So, as we wrap up this explainer, we've basically seen that chemical reactions are just nature brilliantly rearranging its own building blocks. Atoms aren't disappearing, they're just breaking their old bonds and forming entirely new ones. But it really leaves us with a pretty fascinating thought. If mass is always perfectly conserved, and all these elements are just endlessly rearranging themselves into new forms, what exactly is the nature of the unseen energy holding all these entirely new bonds together? That invisible architecture is what truly builds the physical world around us. Thanks for joining me to decode the matrix of matter. Keep questioning, keep observing, and I'll catch you in the next explainer.